Ladies and gentlemen, welcome. Today we are about to embark on a fascinating journey into the world of polymers. But first, let's do a little exercise together. Take a moment to look around you. Raise your hands if you can spot any objects made up of plastic nearby. I see many hands up. Fantastic. It seems like we are surrounded by polymers everywhere we look. This doesn't come up as a surprise though. A significant increase in the plastic percentage has been noted. Polymeric waste amounted to about 20% of the total volume and 8% of the overall weight of municipal solid waste in the USA during 2000, significantly increasing to about 11.7% by 2006. But what exactly are polymers? Well, my friends, polymers are large molecules made up of repeating smaller units called monomers. They're like a chain of building blocks, with each link representing a monomer. If that's not so intriguing, think of monomers as Lego blocks. They can be combined in countless ways to create a wide range of material with varying properties. Now that should be cool stuff, right? All of these Lego blocks are transforming the world around you. Or are they? While polymers have revolutionized our lives with their versatility and convenience, their disposal poses a significant challenge. They have become a fundamental part of our life. Their continuous demand has caused polymeric waste accumulation, consuming massive space and contributing to environmental hazards. Additionally, increasing population, widespread urbanization, and rise in living standards, together with the versatile use of polymers, have made polymeric waste a chronic global problem. Our landfills are overflowing with non-biodegradable polymers, and sadly, a significant amount ends up in our oceans, harming marine life and ecosystems. Imagine this. By the year 2050, it is projected that there will be more plastic in oceans by fish than weight. Yes, you heard that right. This shocking prediction was made by the Ellen MacArthur Foundation. Now, you might be thinking, here you go. Here's another one of these environmentalists who wants us to switch to jute bags and paper straws. I mean, who likes to use paper straws for drinking juices? Well, I understand those feelings. And as someone who used to play with Lego, I absolutely love my Lego blocks. And given their impact on us, I do believe that they deserve a proper disposal. Or shall I say, a proper comeback to the society. Now, because of how widely known this topic is, you would expect many methods developed for managing polymeric waste. One of them being incineration. However, the obvious problem with incineration is that it leads to the unacceptable emission of harmful compounds, greenhouse gases, and obnoxious pollutants. Recycling is definitely a viable option. However, just calling it recycling would be misleading. Recycling does form new products and might even sound like a green process, but it is not cost efficient, requiring high energy for transportation and going through the entire reprocessing to obtain a serviceable product that has a practically less performance level than the original product isn't really an ideal solution. Also, mechanical recycling produces mixed plastic waste, which aren't really of any good use to us. The recycling I am talking about is called thermochemical conversion. Thermochemical conversion is a process that involves using heat and chemical reactions to transform waste into useful products. It is a way to recover energy and minerals from waste in an environmentally sustainable manner. And one of these energy recovery methods is called pyrolysis. The word pyrolysis is derived from the Greek words pyro, meaning heat, and lysis, meaning releasing. Pyrolysis describes the process of breaking down our Lego blockchains with heat. Pyrolysis is carried out in the absence of oxygen with or without a catalyst. To have a better understanding of the process, let's compare it to photosynthesis. Just like photosynthesis, wherein a plant absorbs sunlight, breaks down water molecules, and converts it into energy, pyrolysis breaks down and Lego blockchains with heat. Earlier, I have stated that pyrolysis can be performed with a catalyst. Catalysts, in this analogy, can be compared to chlorophyll. They are substances that facilitate the pyrolysis process, much like how chlorophyll enables and enhances the process of photosynthesis. Without a catalyst, the temperatures required for pyrolysis can be exceptionally high, reaching around 770 Kelvin, which is a significant amount. By using various kinds of catalysts, we can lower the temperatures needed for the pyrolysis process, making it more efficient. Catalysts increase the rate of the pyrolysis reaction without being directly consumed or chemically altered, just as chlorophyll in photosynthesis remains unchanged while aiding the reaction. Great. So we now know about pyrolysis and catalysts. And an obvious name for this process is catalytic pyrolysis. Yeah, it's a bit of a bummer. So, what was the point of all of this? I mean, all of these processes are long known and well researched. Well, the key problem lies in the kinds of catalysts we have been using. Currently, we either use a homogeneous or a heterogeneous catalyst. A homogeneous catalyst reacts with a polymer in the same phase. That is, if the polymer is a liquid, then the catalyst is also a liquid. Examples include aluminium chloride and ferric chloride. Now, it does ensure high catalytic activity, but the process isn't very practical, as after the reaction, it is difficult to separate the catalyst from the final product. A heterogeneous catalyst, on the other hand, can react with the material while in a different phase. It only reacts with the vapors of the polymer. Examples include solid acids, such as clay, and basic oxides, such as zinc oxide, titanium oxide, etc. Now, this process has its limitations too. The disadvantage is that heterogeneous catalysts have a limited ability to catalyze reactions because their surface area is smaller. This limitation results in higher consumption of the catalysts, which are valuable materials. Also, these catalysts are very expensive, so carrying out this process on a large scale isn't feasible, especially considering how high the catalyst consumption is. Yeah, alright, but Mr. Environmentalist, what are you here for? What do you want us to know? What do we take away from all of this? Well, you take away the solution that can potentially resolve all of these limitations and give the deserving comebacks our precious Lego blocks need. I did mention the problem with surface area, right? So if the surface area is reduced, common sense says we increase it. How? Well, this is where I suggest that we use nanocatalysts during the process of pyrolysis. Nanocatalysis, also known as soluble homogeneous or semi-heterogeneous catalysis, can be considered a distinct category that combines the beneficial aspects of both the processes. Nanocatalysts enhance the surface area to volume ratio, promote faster reactions in breaking the carbon-carbon bonds at lower temperatures, denote less energy consumption, and enable enhancement in the process selectivity, whereby higher value-added products are generated with increased yield. It lowers the pyrolysis process energy consumption and provides a longer lifetime to the catalyst system, and the reusability of the active nanostructured catalyst makes it sustainable as well. Whoa. What I simply meant was, this is a sustainable solution. It reduces the amount of catalyst consumed, increases the surface area, reduces the energy consumption, plus it is reusable. Now, you might also think that nanotechnology is a relatively new field, requiring more research. Yes, you are right, but it's important to note that I'm not talking about nanotechnology. I am talking about nanocatalysts. The knowledge of nanocatalysts prevails since the 1950s, even when the term nanotechnology did not exist. Iron, aluminium, titanium dioxide, clays have all been used as catalysts in nanoparticle form for many years. They have been used in environmental protection, solid rocket propulsion, water purification, and the list goes on. They are relatively cheap as well. Palladium, platinum, iron, nickel, and copper-based nanocatalysts are readily available at a reasonable cost. Amazing. But Mr. Environmentalist, I have one last question. How is this information useful to me? How would it impact my daily life? Now that's a very solid question. All of the above information is pretty much useless if in the end we don't know how it would impact our lives. Well, the utility lies in the products formed. Waste plastics can be decomposed and converted into energy in the form of solid, liquid, and gaseous fuels. It produces hydrocarbon compounds such as kerosene as well as low alkanes including butane and propane. Using nanocatalysis to improve the efficiency of pyrolysis, these fuels can be further processed for use in heating systems, kitchen stoves, and smaller vehicles. Liquid oil is also one of the byproducts of pyrolysis. Yes, good quality liquid oil can be produced by simply recovering energy from plastics. With the ever-increasing demand for fossil fuels, the pump price continues to spike up, adding to a pretty bleak picture for fuel vehicle owners. Through oil refinery distillation, this liquid oil can be reused by petrochemical industries and can be converted into diesel as well. To sum it all up, I'd like to quote Richard Feynman. We are trying to prove ourselves wrong as quickly as possible, because only in that way can we find progress. I'm not claiming that I come here with the ultimate solution for a sustainable world. I come here with the vision to bring a change. When I was in 11th grade, reality hit me hard. The spoon-feeding time was over, and I had to prove myself at every instance. That chance was given to me through a chemistry competition. I was supposed to give an idea for managing polymeric waste. Now, obviously, it wasn't a very important topic for me. The 10th grader me wouldn't have cared about it. But this time, it was about proving myself and bringing the change. I researched upon this topic, sat down, and hit the bullseye with Nanocatalysis. Now, my vision is clear and decisive when it comes to addressing this problem and making our world a better place, not just today, but also in the future. With increased consumerism, I feel it is our responsibility as a race to address the problems that float in with it. And I want to lace my journey as a solution finder to address all these problems and find the solutions with this prestigious cohort of SCM Youth. Hope my efforts were polymerizing. Thank you.